Hello, welcome to week 12, the final week in the Digital Electronic Circuits course from nptel. I am Sachin Sampath, the instructor for this problem solving session. Give me a minute to bring up to share my screen. Alright, let me get the questions. Question 1 is as follows. Consider the matrix addressing scheme based memory block shown in the figure below. Let the memory block have 2048 cells. Which among the following is or are the possible values of x and y? So it's a matrix of 2048 cells. And each cell is addressed by a row index and a column index. A row address and a column address. Similar to the elements of a matrix, where if you have a matrix A, its elements can be indexed by 1 1, so first row first column, first row second column, a1 2, etc. Similarly in the second row first column, a2 1, so you use two indices to index the element of the matrix. In a similar way, the cells here are identified by the row address and the column address. If you have x column lines, just give me a minute. If there are x column lines, that means there are 2 power x decoder outputs. Each of which selects one column. Y row lines means that there are 2 power y decoder outputs, each of which selects a row, one row. Therefore, number of unique addresses is 2 power x into 2 power y, which is 2 power x plus y, is equal to 2048. So 2 power x plus y is equal to 2 power 10 is 1024, 2 power 11 is 2048, which will mean that x plus y must be 11. So x is 6, y is 5, or x is 5, y is 6. Out of the options, we have x is equal to 5, y is equal to 6 as option C, and x is equal to 6, y is equal to 5 as option D. Both of them will work. So the answer to this question is both option C and option D. Let's move on to question number 2 now. Consider the memory block shown in figure below. Which of the following correctly represents the write and read logic? We have seen this exact memory block in the lecture, so you can go back and check the lecture videos. The first lecture of this week, lecture 51, I think. It's lecture 56. So what happens in this type of circuit is there are control inputs, and depending on the values of the control inputs, either you will write data onto the memory or you will read data from the memory. Of course, which memory address you're writing to or reading from is decided by other address lines. They have not included those lines in this diagram. First thing here is that if CS bar is 0, then it will perform a, if CS bar is 0, then these buffers are all if CS bar is 0, then the circuit will perform whatever operation you want it to perform, read or write operation. But if CS bar is 1, it should not read or write. So that's the purpose of CS bar input. So it will enable or disable the entire circuit. When CS bar is 0, the circuit is enabled, and when CS bar is 1, the circuit is disabled. OE is a similar control input, but only for the read operation. If OE is 0, then a read operation won't be performed. So even if the other control inputs want you to perform are selected such that a read operation should be done. If OE is 0, it doesn't read anything. So OE controls the reading operation only. CS bar controls both the read and write operation simultaneously, whether you should perform them or not. Then the input r slash w bar will control which of the operations read or write is being done. If r slash w bar is 1, then you will perform a read operation, so you will read some data from the memory. If r slash w bar is 0, then you will perform a write operation, that is, you will give some data at the input lines I1 to I0 to I7, and that particular data will be written onto the memory. The truth table of this is as follows. You have CS, OE and read write as your inputs, and which operation is being performed as your output. So if write is 1, that means you will be doing a write operation. If read is 1, that means you will be doing a read operation. When CS bar is 1, you don't read or write regardless of the value of OE and RW bar. OE and RW bar could take the value 0, 1, 0, 0, 0, 1, 1, 0 or 1, 1 regardless of the values of OE and R slash W bar. If CS bar is 1, read and write both are 0. Next, when CS bar is 0, then read and write the entire circuit is enabled. Now OE will decide whether read operation is enabled or not. When OE is 0, then read operation is disabled, so you will get only 0, 0. And when OE is 1, then read operation is enabled. Now which operation is to be performed is decided by r slash w bar. If r slash w bar is 0, you should perform a write. If it is 1, you should perform a read, but OE is 0 in the second row, so read is not done. Next, when OE is 1, this is the usual operation of the circuit. When r slash w bar is 1, you do a read. When r slash w bar is 0, you do a write. So that is the logic for this control circuit, and that is given in option C. Write is CS bar, OE bar, r slash w bar complement. Read is CS bar, OE, r slash w bar. Sorry, here when OE is high, read does not work. Write does not work, only read operation happens. So let me sort this out. So when OE is 0, you cannot read, you can only write, and you will only write if r slash w bar is 0. When OE is 1, you cannot write, you can only read, and when r slash w bar is okay, when r slash w bar is 1, then you will read. I hope that's clear. I messed up a bit, but looking at the truth table, you should be able to figure out what exactly is happening. Well, first of all, CS bar enables or disables the entire thing. If CS bar is 1, then read write both will be 0 always. Next thing, once CS bar is 0, you look at OE. If OE is 0, you cannot read, you can only write. If OE is 1, you cannot write, you can only read. So when OE is 0, you can only write, and only write is enabled only if r/w bar is 0. If r/w bar is 1, then you don't write anyway. Similarly, when OE is 1, you can only read, and read is enabled only if r/w bar is 1. So that's the logic. In the given PAL circuit diagram, the expressions for W, X, Y, and Z are it is more convenient to label these lines like this. This is A bar, B bar, C bar, D bar. Okay, then the first AND gate is connected to A, B, and C bar. So this is A, B, C bar. Second AND gate is connected to A bar, B bar, and C and D bar. So this is A bar, B bar, C, D bar. So we have W is A, B, C bar plus A bar, B bar, C, D bar. Alright. Then for X, we have the first AND gate is simply connected to A. The second AND gate is connected to B, C, and D. It's B, C, D. So X is A plus B, C, D. Similarly, Y is first AND gate is connected to A bar and B. So it's A bar B plus second AND gate is connected to C and D. A bar B plus C D plus the third AND gate is connected to B and B bar and D bar. So it is B bar D bar. In the same way, you can find out the expression for other outputs also. Z here is X plus Y plus A C bar D bar plus A bar B bar C bar D. Here X plus Y is A plus A bar B plus B C D plus C D plus B bar D bar, which can be further simplified as a plus a bar into a plus b. Using distributive law, a plus a bar b is a plus a bar into a plus b. So it is equal to 1 into a plus b. So it becomes a plus b plus bcd plus cd plus b bar d bar. Next we have cd, b plus bcd will become b into 1 plus cd, which will just become b. So this is a plus b plus cd plus b bar d bar. Next you can write b plus b bar d bar as b plus b bar into b plus d bar, which will reduce to b plus d bar. So it is a plus b plus cd plus d bar. Again, cd plus d bar can be written as c plus d bar into d plus d bar, which is c plus d bar. So x plus y is equal to a plus b plus c plus d bar. Now z will become x plus y plus a c bar d bar plus a bar b bar c bar d, which is equal to a plus b plus c plus d bar plus a c bar d bar plus a bar b bar c bar d. You can write a plus a bar b bar c bar d as a plus a bar into a plus b bar c bar d. So it's a plus b bar c bar d plus b plus c plus d bar plus, and then this d bar plus a c bar d bar can be written as d bar into 1 plus a c bar, so it will become simply d bar. Now this b plus b bar c bar d bar b bar c bar d can be written as b plus b bar into b plus c bar d, which will become b plus c bar d. So it is a plus b plus c bar d plus c plus d bar. Now c plus c bar d will become c plus c bar into c plus d, which is nothing but c plus d. So it is a plus b plus c plus d plus d bar. D plus d bar is 1, so z is equal to 1. So we have found that w is a b c bar plus a bar b bar c d bar, and z is 1. Z is 1 means it can be written as the sum of all minterms from 1 to 15, from 0 to 15. So option D has Z is equal to summation from 1 to 15. Midterm 0 is not included, so that's not correct. Option C is also similar, so that's also not correct. So it has to be option A or B, where Z is equal to 1. Then you can write down you can write down in the canonical sum of products form. You can write down W in that form. It will become AB C bar D plus AB C bar D bar plus A bar B bar C D bar, and just give me a minute. Alright, so this can be further written as AB C bar D plus AB C bar D bar plus A bar B bar C D bar. So this is two terms, minterm 2, minterm 12 and minterm 13. So the right answer is option B. Once we have the Boolean expression, you can always write it in the canonical sum of products form and find out which min terms are present in the Boolean expression. We'll go to question 4. For the circuit given in the figure, the initial condition is V is high, Vf is low, Vg is high, Vh is low, A, B, C are all low. After a while, the state of A, B, and C were changed to A is equal to 1, B is equal to 1, C is equal to 1 for a brief period of time, and was later changed to A is equal to 1, B is equal to 1, C is equal to 0, which of the following correctly represents the final state of D and D bar. So here what A is doing, you can see A is connected to the inputs of these two MOSFETs. So if A is high, that means A bar is 0. So these two MOSFETs are off. So D and D bar are not connected to these terminals. They are connected to these terminals. And since A is high, this will act as an on switch. So it will act as a short circuit. It's connected to F, and D bar is connected to E. Okay. Alright. That is what happens when A is 1. Here we have A is equal to B is equal to C is equal to 1 for a brief period of time. Before it is changed to A is equal to 1, B is equal to 1, C is equal to 0. So both A and B are kept at 1, 1. The next thing we have to see is B. B is the input data bit. B is kept as 1. So as long as the buffer is on, this B will come here. The output will be 1 of the buffer if the buffer is on, and for the buffer to be on, C must be high. So when C is equal to 1, initially A, B, C are all 1. So the first, this whatever is at B, since C is 1, whatever is at B is transferred as output of the buffer. B has 1, so a high value is transferred to the output of this buffer, and that is connected to F. So this F will become high. It will store 1. Okay. And simultaneously next what happens, C is returned to 0. When C is turned to 0, when C becomes 0, the buffer is off, so data is not being inputted, so it is not being written onto the memory cell. Data is being read from the memory cell at this stage when C is 0. So the buffer output is just high impedance, and whatever is stored in the memory cell is being read. And there are two cells here, two MOS circuits here, and since A is 1, the topmost one is selected, and whatever is stored in the topmost cell is given as the output at D and D bar. So we had transferred a 1 to F, that will show up as a 1 in the output here now when C is turned to 0. Also, initially when C was 1 and B was given as the output here, the NOT of that output, which is 0, was given through this MOSFET to E. So E is actually 0 now. And once C is returned to 0 value, this buffer is off. So whatever is stored at E will be given as output at D bar. So D bar is equal to 0. So the answer is C. D is equal to 1. So if I have to write that in words, when A equals 1, transistors 3 and 4 are off, transistors 1 and 2 are on. So data is written to or read from the top cell, that is E and F. When C is equal to 1, the buffer is on and the data at B is transferred or is written onto the memory cell. B is connected to one end of B is connected to transistor 1 and B bar is connected to transistor 2, which act as pass through transistors. So F takes on the value of B and E takes on the value of B bar, that is 1 and 0 respectively. When C is equal to 0, the buffer is off. So data is read from the cell. D is equal to F is equal to 1, and D bar is equal to E is equal to 0. So that is option C. Okay, let's go to question 5. The given circuit diagram of a PLA unit, the expression for F1 and F2 is given by. So the output of, let's write outputs of gate and gate 1 is C bar B A bar. So A bar B C bar. Output of AND gate 2 is A B C. Output of AND gate 3 is simply B bar C bar. Output of AND gate 4 is A C. Now the output of this OR gate 1 is the sum of output of gate 1, gate 2 and gate 3. So output of OR gate 1 is A bar B C bar plus A B C plus B bar C bar, which can be written in the canonical sum of products form as A bar B C bar plus A B C plus A B bar C bar plus A bar B bar C bar, which is the sum of, this is M7, this is M2, this is M4, this is M0. Sigma M of 0 2 4 7. The output of OR gate 2 is the sum of the second, third and fourth AND gates output. So it is ABC plus B bar C bar plus AC, which can be written in the canonical sum of products form as follows, which is the sum of minterms 0 4, 5 and 7. Lastly, F1 is 1 XOR output of OR gate 1, which is equal to output of OR gate 1 complement, which will be sigma m of output of OR gate 1 is sigma m of 0247. The complement of that will be 1356. F2 is 0 XOR output of OR gate 2, which is nothing but the output of OR gate 2, which is sigma m of 0457. And if you see the options, the right answer is option B. F1 is sigma m of 1356, F2 is sigma m of 0457. We are halfway through the session. I need to use the restroom, so I'll come back in 5 minutes. Alright, I'm back. Sorry for the delay. Let's move on to the second half of the session. 5 more questions left. Let me charge my tablet. Okay, we are at question 6. Consider the initial voltages across the capacitors to be 0 volts and the transistors to be N-channel MOSFETs. S1 and S2 are switches which turn on when D and E are high, logic 1. The logic state at output Z when A is equal to B is equal to C is equal to D is equal to 1 and E is 0 is. Now this question for these particular values of A, B, C and D, it's very straightforward. But the actual circuit is DRAM storage element. This terminal A, like we saw in a previous question, will select which of these MOSFETs is on, which of these MOSFETs is selected. So these are N-channel MOSFETs. So when this voltage to the gate is high, the MOSFET is on. When the voltage to the gate is low, the MOSFET is off. So when A is 1, that is a high voltage. When A is high, that voltage is supplied to the gate of the first topmost MOSFET, and the complement of that, so A complement is low, that is fed as the input to the bottom MOSFET. So when A is high, that is when A is equal to 1, the bottom MOSFET is off. So this is off and the topmost MOSFET is on. Second thing, when B is high, the buffer is on and whatever is there at this point is fed as the output to Z. Third input, when C is high, the switch is S1 is turned on. When E is high, the switch S2 is turned on. D is an input. Whenever a C is turned on, C is high, that is whenever S1 is on, that D will be connected to Farhan. We are halfway through, so I'll go through. We are at question 6 now. I'll go through question 6 to 10, and then if you're interested, I'll do question 1 to 5 again later. Okay. So we are at question 6 now. Initial voltages across the capacitor is 0 volts. So here you have 0 volts and here you have 0 volts, and the transistors are N-channel MOSFETs. So this transistor is an N-channel MOSFET, this is an N-channel MOSFET. S1 and S2 are switches which turn on when D and E are high. I think there is a small mistake here. It is not D, it is C. C is connected here. So when C is high, S1 is on, and when E is high, S2 is on. The logic state at output Z when A is equal to B is equal to C is equal to D is equal to 1 and E is equal to 0 is. So they have given the values for A, B, C, D and E. They are asking what is the value of Z. First I'll explain the working of this circuit. I'll explain what each of the inputs does. So this A input, when it is high, that is fed to the gate of the first transistor. Since it's an n-channel MOSFET, the first transistor will be on when A is high. When A is high, this NOT gate will complement that. So when this is high, this will be low. That is fed as the input to the second transistor, so the second transistor will be off. So here in our question they are given A is equal to 1, so this is high and this is low. The second transistor is off, so we can remove that. The first transistor is on, so this acts like a pass-through transistor. That is, it just acts like a switch. So you can replace this by just a wire like this. Okay, that is connected to this wire. Now since 0 volts is present at the capacitor, this will be at 0 volts. Next we have to look at C. The given C is equal to 1 and E is equal to 0. Since E is 0, S2 is turned off. So it is in this position, whatever they have given, it is in that position itself. But since C is 1, S1 is turned on. So this switch is turned on, and whatever is at D, that will come here through switch 1, and that will be the value of this line. So since D is equal to 1 in our case, what will happen is, it's a high voltage. This high voltage will come through this line and it will start charging this capacitor. So this capacitor will slowly charge to high voltage. And also, since B is 1, this B is connected to the control of this buffer. So when B is 1, whatever is here will be given as output of the buffer. When B is 0, then this buffer will be off and Z will be connected to this point. So in our situation, since B is 1, whatever is present at this point is given as the output at Z. Now this was connected to D, so here you have a 1, which is say 5 volts, that will come at this point. So this is also a 1, and that will come as the output of this buffer. So Z is equal to 1. So the output Z is equal to 1. I hope that is clear. If you have any questions, you can ask me. Alright, we'll move to question 7. Question 7 is a theoretical question. It says, identify the true statement. A. Periodic refresh signal is required in SRAM to replenish lost charge across capacitance. B. In one transistor DRAM cell, reading can be destructive due to high parasitic line capacitance. C. 3 transistor DRAM uses a separate capacitor for data storage, whereas 1T DRAM uses parasitic capacitance of MOSFET. D. Both capacitances of a 4T DRAM cell charges when the refresh signal is made active. It is a purely theoretical question, so you will have to look at the lecture material to find out the answer for this. You can refer to lecture 58, and there you will find out that in a static RAM you don't need to refresh the signal. That is the difference between a static RAM and a dynamic RAM. In an SRAM memory unit, as long as the power is on, once you write something onto the memory, it will stay as it is forever. But it is different in a DRAM cell. In a DRAM cell, even if you are constantly giving a power supply, whatever you have stored in it will slowly fade out. So if you have stored a 1, it might slowly discharge. It will be stored in some capacitor or MOSFET. So it will slowly discharge and it might go to zero. So after every few clock cycles, you will have to keep refreshing the value to keep it at whatever value you want. If you want to store a 1 in the cell, you will have to keep charging the capacitor there. So periodic refresh is required in a DRAM cell. And similarly, remaining statements, uh, option B is true. The answer is option B here. In one transistor DRAM cell, if you read, it can be destructive. So when you try to find out the value that is stored, the value that is stored itself might change. So once you read it, they might not be able to read it again. So you'll have to write whatever value you want again and then read it. So that is true. Option C says 3 transistor DRAM uses a separate capacitor and 1T DRAM uses parasitic capacitance. That's false. It's the opposite. 1T DRAM cell will use a separate capacitor and 3 transistor DRAM uses the parasitic capacitance of a MOSFET. Option D says both capacitances of a 4T DRAM cell charge when a refresh signal is made active. That is false. Only one of the capacitors is refreshed. So this is a purely theoretical question. You can refer to the lecture notes and videos. There's no explanation that I can give. We'll go to question 8 then and see what type of question it is. IC2114 is a 1024x4 memory chip. We need dash number of 2:4 decoders and dash number of IC2114 units to build a memory of size 16,384 by 8. The options are 1, 4, 5, 16, 432 and 532. I'll give you 1 or 2 minutes, think about it, and then I'll tell you the solution. An example of this is given in lecture 58. So what we have is a 1024x4 memory chip. That is, there are 1024 memory lines, and in each memory location you can store 4 bits, right? What we need is a 16,384 memory line circuit. So there must be 16,384 different addresses, and in each address you need to store 8 bits. And how do you get this? From the 1024x4 circuit. What you can notice first is, suppose you have two 1024x4 memory chips, and you use the same address select line in both of those. Then what will happen? When you give a particular select input, it will go to a particular memory location, the same memory location in both of the chips, and from the first memory chip you can get 1, 2, 3, 4 bits. From the second memory chip you can get another 4 bits. So if you have two of them next to each other, if you use two same select line for two of them, that will act as a 1024 by 8 memory chip. But this has only 10. Now you can access 8 bits at a time, so that problem is solved. But you have only 1024 locations, 1024 address lines. What we need is 16,000 address lines. So suppose we have two more of these like this. And how to select the address lines will be decided by the decoders. I'll come to that later. But if you have two more like this has 1024 address lines, this has 1024 address lines. If you find some way to code these address lines, to combine these address lines together, that will mean that you have 2048 address lines in total. Similarly, if you have say 16 of these pairs of 1024 memory chips, then how many address lanes will you have? 16 into 1024, which is 16,384, which is exactly the number of address lanes that we need. So by using 16 pairs of 1024 by 4 memory chips, you can get 16,384 by 8 memory chip. So total, how many memory chips did you use? 16 pairs. So 16 into 2, 32 memory chips. Now only problem is how would you address this? So addressing is done by you give a binary number for the address, and then that will use a decoder to select one of these lines, right? So to select, we saw decoders in previous classes. If there are m input lines, you can select 2 power m output lines, one among 2 power m output lines. So if you have 2 power m output lines, you will need m input lines in the decoder. So what we'll do is, uh, to select one among these 1024 lines, the select lines will already be there among the 1024 chip itself. See, 1024 chip itself has some way to select the address, right? So within this 1024 by 4 chip, you already have a way to select one of the address locations. So now you have to select one out of these 16 pairs. So should you get your data from this pair, from the first pair, or should you get your data from the second pair? Should you get it from the third pair? So you'll need address lines to select which among these pairs you get your data from. There are 16 pairs, so you would need I said for 2 power m you need m is to 2 power m decoder will give you m input lines, 2 power m output lines. So if you need 16 output lines that you have to select from, then you would need 16 is 2 power 4, so 4 input lines. So using 4 input lines or 4 bits, you can select one of these decoder pairs, and that is done by a 4 is to 16 decoder. Now the thing here is, they're asking how many 2 is to 4 decoders will you need. So in one of the previous classes we had seen that if you want to get a 4 is to 16 decoder using only 2 is to 4 decoders, you can do it using 5 2 is to 4 decoders. So in essence, to select one out of 16 pairs of 1024 by 4 memory chips, we need a 4:16 decoder. We can get a 4:16 decoder using 5 2:4 decoders. So we have 32 chips and we need 5 decoders. So the answer is option D, 5, 32. That was question number 8. We'll go to question number 9. For the diode based ROM shown below, which of the following is or are correct? Oh, it seems that they have not given the circuit diagram. They might have made a mistake. I'll get the circuit diagram in a minute. Let me see. Okay, here is the circuit. So you have all the minterms here. You can see A bar, B bar, C bar is minterm 0, A bar, B bar, C is minterm 1. So these are minterms 2, 3, 4, 5, 6, 7. So all these minterms, how do you connect them? You connect them using a diode. So the way this diode based ROM works is, uh, wherever there's a diode, that particular minterm is present in your output. Also, if there are multiple diodes, then they will be all together. So that's how this circuit works. That means, for example, Y0, you can see that M7 is connected to a diode, M5, M3 and M1 are connected to a diode. So Y0 will be M0 plus Sorry, this is M1, right? It is M1 plus M3 plus M5 plus M7. So it's sigma 1357. Y1, it's not connected to any of the minterms. There's no diode here. So Y1 is always 0. Y2 is connected to M6 and M2, minterms 2 and 6. Y3 is connected to minterms 5 and 3. Y4 is connected to the minterms 4, 5 and 7, and Y5 is connected to the minterms 6 and 7. Okay, so now we have to compare this with the options, and if you look at option B, Y0 is sigma m of 1357, Y1 is 0, Y2 is 26, then 35, Y4 is 457, Y5 is 67. That is true. So option B is correct. But there's a twist here. You can see that Y0 is the sum of minterms 1357, which are odd minterms, and odd minterms have 1 in their LSB. So whenever the LSB, that is bit number, that is C, is 1, Y0 is 1, and whenever C is 0, Y0 is 0. So you can also write Y0 as C. If you didn't understand what I just said, you can write the K-map of this summation sigma m of 1357 and simplify the K-map. You will find that Y0 is equal to C. So option 1, where it says, not option 1, option D, where it says Y0 is C, Y1 is 0, Y2 is 26, etc., that is also a correct option. So there are two answers here, and it depends on the type of question they have asked. If it's a single choice question where you are only allowed to mark a single option, then if you mark any one of them, you will get full marks. But if it is a multiple answer type question, then if you mark only one of them, you will get only half a mark. So the answer is both option B and D. I hope that is clear. We'll move on to the next question. Question number 10. Again, this question is very direct, and the working of this particular circuit, you'll have to go and look at the lecture uh, lecture 58 on exactly how this circuit works. So they're saying which of the following statements are true. Multiple of them are true. That's why they're saying which of them are true. And first statement, the circuitry performs a write operation. You see that read bar slash write is low. So when R bar slash W is low, it actually performs a read operation. So whichever of these is complemented, that will be performed when the input is low. whichever is uncomplemented, here W is uncomplemented, that is right, that will be performed only if that input is high. So this input here they have given it is low, so R bar will be high, that is read operation is performed. So option the first statement, the circuitry performs the write operation, is false. Second one, the memory block is accessed through address lines X and Y. That is also true. You have X and Y here through which you will access the memory. Then if V2 is high, the voltage moves through pass transistors to transistor Q13 and D out is 0. So you can see here this V2 that will V2 will turn on this. It will make this. It will make that as a pass transistor, and that voltage, whatever is here, will pass through, right? And similarly, it is applied to this terminal. So the exact working of this, you'll have to look it up yourself. I don't remember exactly, but ultimately, what happens in the circuit is if V2 is high, then it will pass through this transistor Q13 and this D out will be 0. Instead of V2, if this V1 is high, then the exact same operation will happen but on the opposite side of this circuit. So this Q14 will be turned on and D out bar will be 0. So you can see that this is an NMOS, so if this is on, it will pull down this D out to 0. So and if this is on, it will pull down D out bar to 0. And when D out is pulled to 0, then D out bar, obviously it will be pulled to high. So the exact working, you will have to look at the lecture to understand how it happens. And you can see that one side you are giving the complement of your data input and the other side you are giving data as is. So whenever this is turned on, this will also be on, so this will act as pass through transistors, and this data, it will be given if data is high, say, that means this Q14 will be off, no, on, so it will be pulled down to 0, the out bar is 0. So and at the same time you are giving data bar here, that means this will be low, so this will be off, it will be pulled to a high value. So whenever V2, both 3 and 4 are true statements, only false statement here is that first statement, the circuitry performs the write operation. In the other type of memory we had seen, SRAM and all, you had R slash W bar instead of R bar slash W. In that case, if R slash W bar, see, W is complemented, write operation is complemented. So when this is low, you perform a write operation. When it is high, you perform a read operation. Here it's different. The read is the complemented control input. So when it is low, you actually perform read, and when it is high, you perform write. So 2, 3, and 4 are all true. So its an answer is option B. Do you want me to go through the first 5 questions, or will you watch the recorded lecture? Since we have time, I'll go through the first 5 questions shortly. So question 1, you have Consider the matrix addressing scheme based memory block shown in the figure below. Let the memory block have 2048 cells. Which among the following is or are possible values of capital X and capital Y? So this is a memory block with cells arranged in this way, right? It's a matrix. So each of these cells can be identified by which row it is in and which column it is in, right? The row and the column will decide which particular cell you are talking about. So it so what does that mean here? So the address of each of the cell is given by the row address and the column address, or the row number and the column number. Here, since you have X column lines and it is passed through a decoder, we saw earlier the decoder will have 2 power X output lines. It will select one among 2 power X output lines. So there are 2 power X columns here. Since there are Y row lines, this decoder will have 2 power Y output lines, right? And it will select one among those 2 power Y output lines. So there are 2 power Y rows here. So the total number of cells will be 2 power Y into 2 power X, which is 2 power X plus Y. But that number, the total number of cells, is equal to 2048, right? It's a 2048 cell memory block. So 2 power X plus Y is equal to 2048. 2048, if you express in terms of powers of 2, we know that 1024, it's easier to remember, 1024 is 2 power 10. So 2048 is 1024 into 2, so it's 2 power 11. 2 power X plus Y should be equal to 2 power 11. That means X plus Y should be equal to 11. So either X is 6, Y is 5, or X is 5, Y is 6. So two of the options are correct, option C and option D. Question 2. Consider the memory block shown in figure below. Which of the following correctly represents the write and read logic? Here there are three control inputs. CS bar is the control input which enables or disables the whole circuit. If CS bar is given as 1, then write and read both are 0. That means you can't read from the memory, you can't write to the memory. So these four. When CS bar is 0, okay, um, the only student who attended the class has left the meeting, so there's no. Okay, when CS bar is 0, that means this circuit is enabled. Then we look at OE. When OE is 0, read operation cannot be done. So read is 0 0. When OE is 1, write operation cannot be done. So write is 0 0. Next, when OE is 0, look at read or write. And if read slash write bar is 1, you can do write. It's 0, you can do write operation. If it is 1, you don't do write operation. When OE is 1, you can't do write. You can do read, but whether you do a read operation or not depends on r slash w bar. If r slash w bar is 1, you do a read operation. If it is 0, you don't do a read operation. So this is the truth table for which operation you are doing. If write is 1, that means you are doing a write operation. If read is 1, that means you are doing a read operation. And only for one particular combination of CS bar, OE and r slash w bar you are doing write, and only for one particular combination you are doing a read operation. For all other combinations, you won't do any operation at all. And using that truth table you can find the Boolean expression, and you will find that it is option C. Write operation is CS complement, OE complement, r slash w bar complement. Read operation is simply CS complement, OE, r slash w complement. You can get the expression from the truth table as long as you understand what the truth table is and how it came from, where it came from. Okay, question 3. A programmable logic array circuit diagram. So they have given you the input lines. All possible complemented and uncomplemented form of the input are already there. So this is the type of symbol you use to show that you have both A and A complement at the same time. So this line is A, this line is A complement, this is B complement, C complement, D and D complement. These two lines are not being used. You could give 1 and 0 if you wanted to. That is a high and low voltage. Here they are not being used. Now a connection is made if there is an X symbol. Okay, so you go through this line. If there is an X symbol, that is given as input. It is a simpler way of writing. Let's say we had A, B, C like this. It is A and B and C. A simpler way of writing this is making connections here, writing this as A, B, C. So this is the same as this. Both are A and B and C, but there are different representations. By writing these crosses, it is simpler to write multiple AND gates. So if you had to write AB plus BC, then in this representation you would have to take wires here and write this as BC and do all this. So it is kind of clunky. If there are more and more inputs, it will be clunkier. So a simpler way to represent it is what we are using. So whenever there's a cross, that particular line is an input to the AND gate. So for the first AND gate, we find that it's connected to A, B and C bar. Second AND gate is connected to A bar, B bar, C, D. So this is A, B, C bar. This is A bar, B bar, C, D. And W is nothing but, here there's an X, so this AND gate is not used. So W is nothing but sum of the outputs of these three AND gates, which is nothing but A, B, C bar plus A bar, B bar, C, D. Similarly, you can find X, Y, and then this will be X plus Y. You can see that here these two additional lines are used for this. This particular line is X plus Y. Here there's a bubble, so this particular line is X plus Y complement. So this is X plus Y, this is X plus Y complement. And you can see in Z, the first AND gate is connected to X plus Y. So it's X plus Y plus whatever you get here plus whatever you get here. Okay. You do this for all the AND and OR gates, and you will get W is A B C bar plus A bar B bar C D bar, X is A plus B C D, Y is A bar B plus C D plus B bar D bar, and Z is finally Z. If you simplify it, you have to do a lot of simplification, you will get Z is equal to 1. And then you have to convert all these expressions into canonical sum of products form. So A B C bar plus A bar B bar C D bar will be written as A B C bar D plus A B C bar D plus D bar. That is, you're writing A B C bar as A B C bar into D plus D bar, because D plus D bar is 1. And then you're using the distributive law. So you'll get the minterms that are there. This is minterm number 2. This is minterm number 12. This is 13. So W can be written as sum of minterms 2, 12 and 13. So it could be this or this. Similarly, you find for, and Z is 1, so it's option B. Suppose this also had 1, you could write the canonical sum of products for x and y, and then check for those also, and whichever option matches for all of w, x, y, z, that is the right answer. So you will find out that it is option B. Next, for the circuit given in the figure, the initial condition is V is high, so VE is high, this is 1, VF is low, this is 0, VG is high, this is 1, VH is low, this is 0, and A, B, C are all low. These are all low. Now after a while the state of A, B and C were changed to A is equal to 1, B is equal to 1, C is equal to 1 for a brief period of time. I'll explain what will happen then. See, when A is equal to 1, this is 0 and this is 1, right? This 1 is a high voltage given to the gate of an NMOS. Similarly, it is high voltage given to gate of this NMOS number 2. When a high voltage is given, it will act as if it's a switch that has been turned on. So it will act as if it's a switch that is on. So it will act as if it's a short circuit. It is connected like this. Okay, and since this is 0, that 0 is being fed to gates of transistor 3 and transistor 4. So both of them will be off because this is n MOSFET, n channel MOSFET. So they will act like an open switch. There's no that means there's no connection here, so it's just open. Okay, and here there is a connection. It is just a straight wire connected here to F, and this wire is connected to E. Okay, now they're saying A is 1. So what happens? You are selecting the topmost MOSFET. So there's no connection here. There is a connection here. Next thing, C is 1. When C is 1, the buffer is on. When the buffer is on, you will get the input whatever is there as is. So you will get B here, and then that is complemented in this NOT gate. So you will get B bar, which is given as input to one side of that. So you have B here and B bar here. They have given B is equal to 1. So B is equal to 1. That means B bar is 0. You can see this B is directly connected to F. So initially F was set to 0. Now that will change to B, which is 1. So this F will become 1. And this B bar is connected to E. Right? So that E will become equal to B bar. So E will be equal to 0. This will become 0. Next, for a brief period of time, and was later changed to A is equal to 1, B is equal to 1, C is equal to 0. So now what they're doing, they're keeping A and B as 1, but C they're turning off. They're changing C to 0. So what will happen is, this 1 is changed to 0. That means this buffer will be off. That means that you won't have any B or B bar. There won't be any connection here now. Okay. Now what happens? But A is still 1. So this connection, these two connections are still there. This one. Right? So now what happens? Whatever is there at F, that will come through this wire and come as the output D. Whatever is there at E, that will pass through this wire and come as the output D bar. So E was changed to 0, F is now 1. So you get D is equal to 1 and D bar is equal to 0. Okay. So what exactly is happening? A will select which transistor is being used. So if A is 1, the upper part is being used. This part is being used. is a, if a is 0, this part is being used. Okay, that's what a does. It will select either the upper part or lower part. Second thing, c, when c is 1, you are writing to the cell, memory cell. So when c is 1, whatever is there at b will go to this f, and whatever is there at b bar will go to e, right? So that is performing an operation, write operation. Similarly, if the second MOSFET was selected, then b, which was here, just comes here, will come and go to h if second MOSFET has been selected, that is if a is 0, and b bar will come here and go to g. So when c is 0, when c is 1, a is 1, select top cell, c is 1, write operation, and when c is 0, it's a read operation. When c is 0, this buffer is off, so whatever is there at f, that will appear as the output at d. Or suppose second MOSFET was selected, whatever is there at h, this will appear at as the output at d. So c is equal to 0 is a read operation. So this is the working of this RAM's, random access memory. Alright, we'll go to question 5 and then end this problem solving session. It is also similar to the previous question. The expression for f1 and f2. So first things first, these lines are c, c bar, b, b bar, a bar. They are connected, the output of the first AND gate. So this line is c bar, this is b, this is a bar, so this is a bar, b, c bar. Similarly, this is a, b, c, so this is a, b, c. This is b bar connected to c bar, so this is b bar, c bar, or b complement, c complement, however you like to call it. This is a, c, so this is a, c. This, if you want to write in canonical form, it will be a plus a complement into b complement, c complement, which is nothing but a, b complement, c complement plus a complement, b complement, c complement. Similarly, ac can be written as abc plus ab bar c. Okay, next thing, the OR gate. For the first OR gate, you are connecting the outputs of 1, 2 and 3, the AND gate 1, 2 and 3. So output of this first OR gate is a bar b c bar plus abc plus b bar c bar. Output of the second OR gate is you're connecting second, third and fourth AND gate output, so it's abc plus b bar c bar plus ac. And finally, f1 is first input of this XOR gate is here, it is connected to a 1, so it is 1 XOR the output of first OR gate. We know that 1 XOR a is nothing but 1 bar a plus 1 a bar. 1 bar is 1 complement is 0, so it is simply a complement. That is, this f1 is nothing but the complement of the output of this OR gate. Similarly, f2, it's connected through an XOR gate. The first input is 0, second input is output of the second OR gate. So 0 XOR any number, say z, is 0 bar z plus 0 z bar. 0 bar is 1, so it is 1 z plus 0, which is nothing but z. So when you XOR with 0, you'll get the other input as it is. So f2 is nothing but the output of the second OR gate. So you can find that out. The outputs of the AND gate are these, and then using that, the output of the OR gates are these, this one and this one. You can write it in the canonical sum of products form, and you will get summation of minterm 0247 OR gate output of the second OR gate is summation of minterms 0457. Now we saw that F1 is the complement of output of first OR gate. So F1 is the complement of 0247, which is nothing but 1356. But the output of the second OR gate is given as it is without complementing, so F2 is simply 0457. And if you compare with the options given, it will be 1356 and 0457, option B. So that is how you solve these types of PAL and PLA problems. Okay, I have covered all 10 questions today. Hopefully you'll be able to understand everything. There will be one more session next week, just a short 1 hour session. I'll just revise everything. Maybe I'll try to solve a few questions from a gate paper. We'll see. Yeah, I'll take recent few gate papers, and only the problems related to digital electronics, I'll pick them out and solve them in the next session. That'll be for 1 hour only next week, same timings on Saturday. That's it for today's class. Thank you for attending.